Hello and welcome to another in the Space Oddities Astronomy Basics series entitled What is a Black Hole? In this first part we're going to ask the questions how are black holes formed and what's inside them. Black holes have long captured the public's imagination, mainly due to their mystery and popular perception that they are destructive, ravening beasts which destroy anything in their path. Films like The Black Hole and Event Horizon have perpetuated the idea that black holes are incomprehensible engines of destruction, dark destroyers of galaxies, the very embodiment of evil. The word black, of course, immediately invokes an image of something unknowable, dark, brooding. Black holes are creatures of the night, stirring our ancient primeval fears about the absence of light and its indelible association with death. Given these negative associations, it's hardly surprising that there is a whole plethora of myths and misunderstandings associated with black holes. Fed and amplified by popular media, these often drown out the actual science behind black holes. Despite the basic fact there is still much about them we do not understand. As astronomical objects, we do know a surprising amount about black holes. We know how they form, how they behave, and roughly how they work. We see the effect they have upon objects around them. We can measure how their gravity behaves exactly as predicted by Einstein. We have at least a basic idea of what lies inside them. So let us start our investigation by asking a basic question. How do black holes form? Astronomers categorize black holes into two main groups. The first is stellar mass black holes with masses ranging from around 5 solar masses up to 100. The second is supermassive black holes found at the centres of most galaxies, with masses which can be measured in billions of solar masses. There is no agreed minimum mass for supermassive black holes, which relates to what we know, or rather what we don't know, about their formation. The most massive black hole we've yet discovered is in the heart of a quasar and is designated TON 618. It has an estimated mass 66 billion times that of our Sun. Between stellar mass and supermassive black holes, it's believed that there is a population of so-called intermediate mass black holes. They should possess at least 100 solar masses. However, as yet we have no firm observational evidence for these objects, although logic dictates that they must exist. It seems unlikely that, in terms of mass, there are no black holes between 100 solar masses and the millions of solar masses we associate with the lightest supermassive black holes. Stellar mass and supermassive black holes are created in different ways. Let's see how. A stellar mass black hole is formed when a star with at least around 7 times the mass of the Sun ends its life in a cataclysmic supernova explosion. Blowing off its outer layers, the core of the star is crushed by gravity so much that its very atoms are squeezed into a tiny point and cease to exist as matter. The mass of the core is still present in this tiny point, which is known as a singularity. What is left behind after the supernova is an immensely strong gravitational field generated by the mass that the core of the star possessed, which we call a black hole. That mass is now concentrated into a point possessing, according to the maths, infinite density and zero volume. We do not possess the language to describe exactly what happens at the singularity, as all our laws of energy, gravity and time cease to apply there. The whole process from the supernova explosion to the formation of the black hole takes only a few seconds. Afterwards, the black hole is orbited by a spinning disk of debris from the explosion, which is known as the accretion disk. This debris is sucked into the black hole like water disappearing down a plug hole. Supermassive black holes are found at the centres of most galaxies. Their origins are hotly debated. With such vast mass, which can be up to billions of times the mass of our Sun, they cannot have formed in the same way as stellar mass black holes, simply because even the biggest stars have masses measured in only thousands of solar masses. We believe that there are two possibilities as to how they formed. The first possibility is that supermassive black holes are formed by the successive merging of stellar mass black holes. That is to say, two black holes of stellar mass merge, and the resulting black hole then merges with another black hole, which itself may be the product of a merger, which then merges with another black hole, and so on in a sort of hierarchy. After each merger, the resulting black hole has nearly twice the mass of the two that merged, eventually reaching what we would call supermassive. Here you can see how it would work. Stellar mass black holes merge to form intermediate mass black holes, which then in turn merge to form a supermassive black hole. It's worth pointing out that each merger may involve more than two black holes. There may be triple or even quadruple black hole systems which merge. We just don't know at the moment. While this idea for the formation of supermassive black holes sounds promising, it has a few problems. The James Webb Space Telescope, or JWST, has observed supermassive black holes in the infant universe existing in early galaxies just a few 100 million years after the Big Bang. These are all infant galaxies, as seen by the JWST just several 100 million years after the Big Bang. Each is thought to contain a supermassive black hole, which are too young to have formed from a succession of mergers because there simply wasn't enough time. It is believed that black holes can orbit each other for millions of years, very slowly and inexorably, drawing closer together until they merge. You can see that this would take an exceptionally long time to produce even a lightweight supermassive black hole, yet, just 700 million years after the Big Bang, the JWST has found a black hole with 40 million times the mass of the Sun. The figures just don't add up if we postulate that it was formed through mergers of smaller black holes. Perhaps a more likely explanation is that supermassive black holes were formed from the spontaneous collapse of giant clouds of hydrogen in the early universe. These clouds may have merged to possess enough mass for the cloud to exceed a limit known as the Tolman-Oppenheimer-Volkoff or TOV limit, which is the maximum amount of mass an object can possess before it collapses into a black hole. Assuming these clouds of hydrogen were plentiful in the early universe, which they surely were, they could account for supermassive black holes forming so soon, in astronomical terms, after the Big Bang. It may be that both processes had a part to play in the formation of supermassive black holes. It's an area of intense research. One big question astronomers would dearly like to know the answer to concerns the relationship between a supermassive black hole, or SMBH, and the galaxy which surrounds it. Did the SMBH form first and then the galaxy then form around it, or did the galaxy evolve first and its centre then collapse to form an SMBH? At the moment we don't know because it's a sort of chicken and egg situation, but one intriguing fact has emerged during the last decade or so. A supermassive black hole can influence the development of a whole galaxy, controlling the rate at which new stars form because of the influence of intense jets of radiation emitted from the vicinity of the black hole. So there is a deep relationship between the co-evolution of a supermassive black hole and its host galaxy, which we are only just beginning to understand. Now let's turn our attention to the structure of black holes, which are probably the simplest objects in the universe. They consist of a boundary called the event horizon, and at their cores there is something known as the singularity. And that's it in terms of structure. The event horizon is not, however, a physical boundary. It's simply a place, a distance from the centre of the black hole, where any object crossing it can never leave again, because to do so would entail that object travelling faster than light. In a nutshell, it's the point of no return. Nothing beyond the event horizon can ever leave the black hole, including light, and this is why black holes appear black. What happens inside the event horizon can never be observed because no information can escape. This means that if somebody were to fall into a black hole, they could never tell anybody outside the event horizon what they saw. Because of this, we can never know exactly what happens inside a black hole. We have to be guided by theory only, with no way of actually testing our theories. The singularity should also not be thought of as a physical thing. Like the event horizon, it's a place rather than a thing. There, all our laws of physics cease to apply. Everything we currently know about time, space and gravity stops being meaningful. The singularity represents the place where all the mass of the black hole is concentrated into a point of infinite density and zero volume, and we simply have no maths to describe what happens in such a place. Obviously, talk of infinite density packed into zero volume does not sit well with astrophysicists, so we believe that in reality such a place does not exist, even though it does in Einstein's maths. To understand what is there, we need a theory of quantum gravity, which will unite Einstein's relativity with quantum mechanics. But relativity, which deals with massive objects behaving under gravity, and quantum mechanics, the behaviour of particles at the tiniest of subatomic scales, do not talk to each other. They are simply not compatible. A quantum theory of gravity still eludes scientists after many decades, but the quest goes on. We assume such a theory must exist because it's inconceivable that there are two sets of laws which govern the universe, one for large objects and one for subatomic particles. Somewhere the two must meet, and that is where we will find our quantum theory of gravity. It's like having two house keys of very different design, only one of which will open any single door, but knowing somewhere there is a door that they will both unlock. Until we have that quantum theory of gravity, what happens at the centre of a black hole will remain a mystery. Well, that's about it for now. I do hope you have enjoyed the first part of our introduction to black holes. Do have a look at our other videos in the Astronomy Basics series. You will find them in a playlist of the same name on our channel. If you have liked this video, please consider subscribing to our channel, liking the video, and perhaps leaving a comment with your feedback, which is exceptionally valuable to us and will enable us to improve our content. Don't forget, if it's happening in space, it's happening on Space Oddities. Thanks so much for watching.